So our project is cooling and dehumidification for indoor growing. And so due to the increasing complications of global warming has in the agricultural community, there's currently different farming methods being researched. One aspect that is being explored in this project will be the self-sufficient indoor growing system. And so this can be achieved using a control box that will maintain ideal growing conditions for plants. One benefit of this device is that it's applicable to the average person, so they'll be able to this device will be able to be used continuously and efficiently for growing plants. This will essentially be able to help the user just make it easier for them to grow plants. There will be no root rot or susceptibility to diseases. And so provided a $700 budget with a production time from September to May, this device has to be able to measure the latent sensible cooling loads, as well as control the pH and the nutrient levels of the hydroponic tubes. It also has to have an alerting system, and we'll be using a Raspberry Pi camera to be able to monitor the plant health.
Okay, so our conceptual design, we will have a control box that will house 2 linear actuators and a peristaltic pump. The peristaltic pump will be connected to a cylindrical reservoir, which will house the nutrient solution, and 2 syringes will be acted upon by the linear actuators, and that'll dispense the acid or base solution. A single Raspberry Pi with the addition of Pi plates will be used for the temperature and humidity sensors, pH sensor, camera, linear actuators, and peristaltic pump. Housing for the linear actuators, Raspberry Pi, and Pi plates will be 3D printed using PLA. The control box will be placed in the greenhouse using hose clamps, and it will be purchased from Amazon. And those are the objectives which we mentioned before. pH sensor and temperature humidity sensor will be connected to the Raspberry Pi to gather the data needed to let the consumer know the conditions of the system. A variable speed dry fan will continuously run and be adjusted based on the data by the sensors. This will maintain the temperature of the system. The Raspberry Pi camera will take pictures of the plant throughout its life, and it will be sent via email to the customer. The temperature and humidity data will be gathered and used to calculate the latent and sensible cooling loads of the system using an energy balance equation and Python. The pH sensor will give feedback to the Raspberry Pi where the linear actuators will adjust the pH accordingly, and every 2 weeks the peristaltic pump will dispense nutrient solution. So throughout the semester we had a few different designs, and so one of them had 3 linear actuators, and it was reconsidered because of how much space it might take with also having another syringe added. So we opted to use a peristaltic pump and 2 linear actuators, which would save some space. We also considered using both Arduino and Raspberry Pi to control the subsystems, but it was going to end up being more complicated, and using just a Raspberry Pi, we can only use Python, so we stick to one programming language, which would be easier for the whole group. And so with the additional space created and the usage of just a Raspberry Pi, the control box can be filled efficiently and with sufficient room for wiring. And this final design checks off all of our design constraints and decisions. And if brought to market, the control box can be sold as an extension of the greenhouse, which will allow all levels of plant growers an easy way to grow all types of vegetation.
Detailed design. So for the latent and sensible cooling loads measurements, the temperature and humidity sensor that we're using is the DH22, and we're using this model because it has a ±2 relative humidity and a ±0.5 temperature accuracy. And when the data is collected from this device, it will be sent to the Raspberry Pi to be analyzed. And if there's any correction that needs to be done, that information will be sent to the fan to be corrected. So for the variable speed fan, it will receive a command from the Raspberry Pi, and if the temperature or humidity is high, so basically the fan will help out to lower that temperature or humidity to the temperature or humidity that we want it to. So for the Raspberry Pi, which is our brain or the brain of the control box, Python codes will be used to control the variable speed fan and the temperature and humidity sensors. So for the energy balance, we are using these equations to find the enthalpy, so that with that information that we find, we are be able to calculate the latent and sensible cooling loads of the system.
So the Raspberry Pi will include three components, which will include the peristaltic pump, the linear actuator, and the pH sensor. The linear actuators will be connected to two syringes, which will contain pH solutions and will respond to the Raspberry code sent to the correct pH level in the water. The lettuce plants will grow best between 5.8 and 6.2 pH range. The peristaltic pump will be connected to the plant nutrient solution reservoir, where the pump will release the nutrient in the water every 2 weeks. And lastly, the pH sensor will be submerged in the hydroponic system, which will take the pH reading level, and each reading will be sent to the Raspberry Pi to activate the linear actuator.
So we'll be using an alerting system using a Raspberry Pi camera in the first iteration of the control box. The camera will essentially take a picture every single day, and it'll be sent through the Raspberry Pi, and then you'll receive an image via your email. And so the user will then make an assessment based on these pictures, whether the plant needs more water, more nutrient solution, or more light. And so you can see here in the flow chart, the Raspberry Pi camera captures the image, goes to the Raspberry Pi, the stored image gets sent to the email, and you will see the image in your inbox.
3D printing will be only for the housing for components inside the control box. The components that currently need housing are the linear actuators and the Pi board with the Pi plates. We have selected these parts to house because the housing are unique and relatively simple to manufacture. For example, the Pi board has an additional Pi plate and the actuators have moving parts. Also, the housing for these components cannot be readily purchased. All other components are purchased instead of manufacturing them, like the control box. This reduces the time using the 3D printer and decreases the likelihood of defections during 3D printing. The main manufacturing methodology will be to break up the housing into several pieces. For example, there will be a top cover and a bottom cover for the Pi board.
So currently, the hydroponic system is being manually controlled, with the pH levels and nutrient distribution being monitored. The team is also currently monitoring the lettuce growth and making adjustments to the system as needed, with members inputting the pH levels and taking pictures of the plant growth in an Excel sheet to monitor the data. A final design for the control box was chosen and modeled using CAD, with the parts list being compiled and ordered, awaiting the parts to arrive next semester. Tasks were distributed among the team, with each team member being responsible for a different subsystem, such as the linear actuator, pH sensor, and temperature sensor, to name a few. And within each subsystem, there's other tasks, such as writing code to run each subsystem, as well as running simulations and testing their functionality. With our finalized design, assembly will begin, and the control box will be implemented into our hydroponic system. Some future tasks include to continue work on the subsystems, and within that, it's troubleshooting the code and beginning the implementation pending the arrival of the parts. Also, the implementation of an app as a part of our feedback and recognition system, and 3D printing the Raspberry Pi housing. We also plan to assemble the first prototype for the control box next semester as well as testing our Python codes for the temperature and humidity sensor, the pH sensor, the Pi camera, the peristaltic pump, and the linear actuator. So this is the Gantt chart for fall semester. Continued, as you can see, it has every team member's tasks and they're all color coded. And this is our chart for the upcoming semester. Thank you.